Having observed water level versus clock time as water flows out of the cylinder, we get data points on a graph of water level y versus clock time t. These data points will be clustered around some sort of a curve. The curve gives you the actual behavior of this system, the actual behavior of the water level as a function of time. We don't know exactly where that curve should be. We have uncertainties in our measurements, but it's probably going to go somewhere kind of along the middle of the sequence of data points. And there are analytical ways, analytical methods based on calculus for determining the function that best fits these points, if you know what kind of function you're looking for. Okay, we don't worry about that right now. We're just going to develop a little bit of what really happens here. So, if this is your depth versus clock time, there is some depth or vertical position, water level. The water level, the level of the hole, the level of the water when the water stops flowing out of the container, when the water level drops to that of the outflow hole. So, obviously, the water level is going to stop when it gets here. And obviously, even though our data doesn't really tell us, our curve isn't going to really tell us exactly when we hit that point because of surface tension and dribbling and dropping behavior at the very end of this process, we should be able to infer where that point would occur if the fluid was completely ideal. Now, this behaves very much like an ideal fluid up to the very end. So we get a very good predicting model here. You don't necessarily know what I mean by all of that, but don't worry about it. Okay, so we get this graph. Now, what kind of a graph is this? Well, for reasons that I kind of outline here, for an ideal fluid, we expect this graph to be a quadratic function, the graph of a quadratic function. A function of the form y equals at squared plus bt plus c. We can test, and I'm not going to get into the reasons for all this at this point. These are things that can be proven, and we will look at proving them. In the first place, if we know where the vertex is, then we have the property that if we put a point here, and another point halfway between here and the vertex, the y-coordinate at this point, that is the water level corresponding to this time, the time that corresponds to this point, is going to be greater than the water level at this time. And the ratio of this level to this level will be the same as the ratio we get between this difference in the levels and the difference we get if we go again halfway toward the vertex. So if we're having the distances, and these aren't really distances, they're time intervals, but if we have the time intervals between each point and the vertex, these distances here are going to be in constant ratio. The distant ratio of this to this, the ratio of this to this. The difference in the levels. This being the level of the hole. Again, we will develop this. Just want you to get the idea that there are tests that allow us to see whether the behavior really is quadratic. And there are all kinds of uncertainties to take account of and so forth, but we'll deal with those in a systematic manner. Okay, another test is that if you have the curve and mark off your y or your t-axis at equal intervals, and at each interval you take the point on the graph and draw the tangent line to the graph at that point. So at this point, here's our graph point, tangent line here. At this point, graph point, tangent line at that point. Here, tangent line at that corresponding point. That if these are equal intervals again, the slopes that you get form a linear sequence. meaning that each one differs from the one before it by the same amount. To the extent that that's true, the graph is quadratic, and you don't even have to know where the vertex is. Okay, now, if the graph is quadratic, and again, this is not something you're going to totally comprehend right now, just giving you an idea where we might go. The flow rate at which water comes out, the number of cubic centimeters per second, if you wish, or, well, yeah, that's good enough. Flow rate, say in cubic centimeters per second versus time. Flow rate in whatever volume unit you might want to do. You do it in cubic millimeters per second, cubic centimeters per hour. That would be a flow rate. Whatever units you use, your flow rate is going to be a linear function of clock time if this graph really is quadratic, and it's easy to prove that. We kind of do right here, but not really. There are several connections to make, geometric connections and so forth, but it's fairly easy to get from here to here. Now, another thing, this flow rate should be linear, and as it turns out, the horizontal range of the flow, the distance the flow goes before it crosses that ruler, distance in this direction before it crosses the level of the ruler, the distance it travels in falling that far, whatever the distance is, should be a linear function of clock time. And this comes out because the exit velocity is proportional to the pressure of the fluid at the point of the outflow, which is proportional to the difference between the water level y and the level of the hole. And that gives us what's called a differential equation. I'm not going to read to you. All I'm going to say is, here be physics and calculus, and beware. Okay? We aren't into physics and calculus at this point. There are reasons from physics and calculus that this should be linear, and I haven't delineated all of them. There's also the idea of the projectile behavior of the stream. We're not going to talk about that. We're not talking about physics, although this is a physics dictated situation. We're talking about the mathematical aspects of this system, okay? So, if y is quadratic, and this is the form of a quadratic function, and we should know this if we've been through a precalculus course. The difference quotient, something else we learned in a precalculus course, is obtained just by determining the average rate of change excuse me, of this function between clock time t and clock time t plus delta t. So, if we evaluate the function excuse me, at t plus delta t and at t subtract the 2, we get the change in the value of the function, which will be the change in the level of the water. We divide that by t plus delta t minus t, and of course that's just delta t, and we're dividing by the time interval. So we get the change in the depth divided by the time interval, which is the rate of change, the average rate of change of depth with respect to time. Now, thought I had a white piece of chalk here because there's something I need to fix. That T wasn't quite crossed, and that was bothering me. Okay, now if we evaluate this difference quotient, again, something that we should learn in a precalculus course, but if we didn't, it's real easy to learn. That's going to equal, well, I got some dots here, there are a couple of steps, but that comes out to be equal to 2at plus b plus a delta t. And as t delta t approaches 0, this approaches 2at plus b. Now, as delta t approaches 0, this average rate approaches what we call an instantaneous rate. Now, that's something we need to think about. That's something you talk about in a calculus course, but we want to talk about it a little bit in a precalculus course, so it's not a shock when we get to calculus. It's not that big of a shock, but makes calculus a lot easier if we talk about that in this course. Okay? So, what we get then, the 2at plus b, is the instantaneous rate of change of this function. So we write that instantaneous rate of change of y equals f of t as y prime equals f prime of t. This is the way we read it. We put this apostrophe on it. And now this represents the rate of change function for this function. And that rate of change function is 2at plus b. The instantaneous rate of change of depth with respect to clock time, that's what this tells you, the instantaneous rate of change, as I've just said, and that's also the slope of the tangent line at the point t, f of t. That is, if this is our graph of f of t, put in any value of t, go up here, do your tangent line, the slope of that tangent line, if it's done accurately, has to match what you get if you evaluate 2at plus b. So, slope of the tangent line, rate of depth change. Now there's a month of calculus in this whole discussion, but this little bit of it is pretty easy to understand and grasp. You're not going to understand and grasp it from what I've just said, but it's fairly easy to grasp. If you work through the details, they aren't particularly difficult. The big payoff here is that this pretty much proves what I said here. I say pretty much, there are plenty of connections that need to be made, but the basic underlying reason, a quadratic function here gives you a linear flow rate, a quadratic depth function gives you a linear flow rate for a uniform cylinder, is just this. Notice that 2at plus b is a linear function. Now, of course, if you've been through precalculus and haven't learned to classify functions, you're not really sure what I'm talking about when I talk about a linear function versus a quadratic function. So that needs to be clarified. But that's, again, that's pretty easy. It gets overlooked. You lose the forest for the trees. When you're doing the homework, you're working out all the algebra. It's somewhat difficult to do that while you're learning the course. But that's why we need to maybe have a little transition between precalculus and calculus.